And welcome, grade 10s. Today we're going to do our last session on wave, sound and light, and we're going to look at the electromagnetic radiation. Now, this is a really nice section. It sort of isn't sound, it is definitely not sound, and it's sort of light but not quite. And what we're going to do is we're going to look at the fact that electromagnetic radiation is actually really important. You just don't experience most of it. That you think you're not experiencing it. Light is such an important part of the spectrum. And what we're going to look at today is we're going to look at some key things that are important. And number one, we're going to look at the properties of light. Light is a very, very important part of the electromagnetic radiation. We're then going to look at the wave nature, or the wave-like nature of light. And this is a bit of a debate between scientists that has been going on for 300 years. And I'm not sure it's ever actually going to be ended. I don't think anyone's ever going to make a complete decision as to what light really is. But we are going to look at the wave-like nature of light and why we think it is that. We're then going to look at the electromagnetic spectrum, of which light is a very small part. Then we're going to have to look at the penetrating ability of the electromagnetic radiation. In specific, we're going to look at UV radiation. You all know about UV radiation, and you all know, especially with global warming and everything else that's going on in the hole in our ozone, that we need to be using things like sunblock and sun cream to stop us from getting things like skin cancer. And you know, it doesn't actually matter what the pigment of your skin is. That's a very important thing to consider. So we're going to look at those sort of things and why UV radiation actually burns us. Then we're going to look at, when we end today, we're going to look at the particle-like nature of EM radiation. And in fact, light also has a particle nature. And we're going to discuss a little bit why we think it has that particle nature. Unfortunately, for you in grade 10, we don't look at the experiments that actually define particle nature for us. But we are going to hopefully explain it a little bit more for you so it makes a little bit sense. So that's where we're going to go. So let's just jump right in there and talk about the special properties of light. Now, light, you've dealt with lights, okay? And we're very grateful we have light, especially in the morning when we wake up. That's where summer's really nice because we have early mornings. You don't have to wake up in the dark, which is really horrible in winter. But we have these early mornings, we go outside, and we can see the world around us because we have light that comes from the sun. At home, we all know what it's like to experience a blackout where we don't have electricity for whatever reason, and then we have to study or work by candlelight. We know that's just not fun, but we can still do it because we have light. So light's a really important part of our lives. I'm hoping you also all realize, after a rainstorm, the most prettiest thing to see is when we see a rainbow in the clouds or through the sun, and they're actually really pretty to see. And what that rainbow is showing us is the spectrum of colors, which are red, orange, yellow, green, blue, indigo, and violet, which you don't need to know. But we have that beautiful spectrum of colors, and that is part of what we call the spectrum of light, where we can separate light into these beautiful colors. Think about when you go to the paint store and you've decided you want to repaint your bedroom, and you don't want just a normal shade of pink or blue or purple. You go to the paint store and they mix a brand new shade of color for you. And you go, oh, that's exciting, because only your room would have that color, and your mom and dad are probably going, do we have to? But it's okay, you're a teenager, you're allowed to. But we have this huge spectrum of colors. Think about when you go to the shops to do clothes shopping, or every season, especially for the girls, there are different colors that are in. And in fact, at the moment, the colors that are in are neon and bright. And as part of the older generation, I struggle with those. But hey, you guys like it, and everything glows in the dark. And that's all part of the spectrum. It's all part of this huge color spectrum that we get. But that's not all that's special. So by spectrum, we're talking about the colors. And here, I'm really talking about visible light, the stuff I can see. Even on our set, you can see a whole bunch of different shades of blue behind me and the red for the X. So it's great, we like that. But what about the speed of light? Now, this is actually a little bit of a debate at the moment in the scientific community. The speed of light is always been considered to be the maximum speed that anything can travel at. And it's specifically 3 × 10⁸. Now, that has been the ultimate speed of light. When you watch sci-fi programs and they talk about traveling through the universe, they often talk about traveling at speeds greater than the speed of light, which is what makes it science fiction. The honest truth is no one really knows what would happen to the human body or matter if we should be able to travel at the speed of light, and that's what Einstein was talking about with his famous equation E equals mc squared. But at the moment, there really is a debate in the scientific community as to whether they've discovered a subatomic particle, a particle inside the atom, that is traveling faster than the speed of light. Huge debate. This is going to turn the scientific community on its ear. So everything's going to get turned upside down if they find that it really is. But for now, we're going to say this 3 times 10 to the 8 upper limit, excuse me, of anything. Nothing can travel faster than the speed of light, which is still incredibly fast. Okay? Then, now we get to the fun part. Light has a wave nature. What does that actually mean? Well, waves are, think about ocean waves. We have our waves coming, they're crashing along the sea. When you watch waves come in through the ocean, I'm sure you've noticed the wave changes, and the wave gets refracted, its speed changes. We can only do that with waves because they're continuous. Okay, and the wave comes along and now it's losing depth and can't go as deep as it was, so it changes its speed because we change its wavelength. Okay, we can't change its frequency. Frequency is set by the source. So the wave's wavelength changes, so its speed changes. But only waves do that. Reflection. You see reflection, think about it, in the morning you get up, you have your bath or your shower, you decide you need to look good for school, and that's very important. You brush your hair, you brush your teeth. You do that in a mirror. We do it in a mirror because we can see a reflection of our image, which is actually quite important. I like being able to do that in the morning, just make sure everything's in place. The reflection means that the light that comes to me gets reflected off me onto the mirror reflects an image back to me, which I can then see. That's because it's a wave, all right? And not only do we get things called diffraction. You're not going to do diffraction too much this year, but with diffraction of light, what that means is the light can spread out. It goes through a little gap and it spreads out. For example, you're driving in a car at night and you see headlights coming from the car coming towards you, and through the windscreen it looks like the headlight gets all fuzzy. It's not a nice little round dot from the headlight, okay? But it gets all fuzzy. That's because of diffraction, okay? Now, that happens because light has a wave nature. But at the same time, light is also what we call a particle. It has a particle nature. For example, how do I know it can have a particle nature? Think about a squash ball. Okay, when you play squash, you take a tiny little round rubber ball and it gets hit against a wall. When it gets hit against the wall, it bounces back off the wall. That is a form of reflection, because that's what's happening when a wave gets reflected. It's bounced off a surface. That means that now we have this situation where, well, light definitely behaves as a wave, but then it could also be a particle because it can also be reflected. Okay, particles, refraction can't happen as much, but for example, a good place of where we could see refraction is in a crime lab. I'm sure you've all seen programs like CSI and that sort of thing, where they test fire a gun. When they test fire a gun, they shoot the bullet into a container of water or into a special gel. Now, the nice thing is when you watch it, they film these really nicely, is you see the gun slow down. Not the gun, sorry, the bullet. The bullet slows down as it gets into the water or through the gel. Now, what's actually happened there is we've changed the speed of the bullet. That is refraction. We've changed its speed. That means this particle has been refracted. So if light can be refracted, then that means it can also be a particle. And this is where the debate is. The honest truth when it comes to this, grade 10s, is we cannot set up experiments where we can 100% prove it's a wave or a particle at the same time. We can either do an experiment to show that it's a wave, or we can do an experiment to show that it's a particle, but we can't do both together. So scientists have really come up with this and said, well, you know what, for now, we're going to say that light has a dual nature. So between these, it has a dual nature. Now, what that means is it is both a wave and a particle at the same time. A little bit out there when it comes to thinking about these things, but we're just going to keep that in focus. The nice thing for you, and at school level and even beyond, is we're never going to do anything where I expect you to remember both. So we're either going to deal with it as a wave or we're going to deal with it as a particle. But we're not going to combine the two because it's actually quite a difficult concept. And it's a little hard to get your head around that one. Okay, so that's one of the special properties. Another special property of light is it doesn't need a medium. Now, how do we know that? Now, we've discussed the fact that sound definitely needs a medium. I have to have something, otherwise I can't hear. But what about light? Our main source of light comes from the sun. The sun is thousands of kilometers away from us in space, in a vacuum, essentially. Space isn't 100% vacuum because there are particles in space. There's planets and stars and all the rest of it. But the sun is in a vacuum, essentially. The sun has its little chemical reactions happening. It's fusion and all sorts of things. It's a nice big nuclear explosion. We're thousands of kilometers away, but as the Earth turns towards the sun for us, where we are on the planet, we experience light. How does that light get to us? There's no medium, which tells us light doesn't need a medium. Light can travel through a vacuum. But this is what makes light really, really special. Light can travel through a vacuum and it can travel through substances, which is a good thing for us, because if light couldn't travel through a medium, light would hit our atmosphere and stop. Then we would still be in the dark. So we're very grateful that light has this wonderful property that it doesn't need a medium, okay? Now, the last nice part about light is that it's part of the electromagnetic radiation. Throughout this series, just to make life a little bit easier, we're going to use EM as a little bit of an abbreviation. It's simply to make our life easier when we write things down. Why is this nice for us, that light is part of the electromagnetic radiation spectrum? Because we cannot see the beginning of the electromagnetic radiation where we have very long waves, and we can't see the other end where we have very short waves, because we just can't. It's just not physically possible for us to actually see them. We're not designed that way. But we know that light's part of that spectrum, which means any experiments we do with light, anything that we discover about the properties of light, the things light does, we can then say, well, you know what? If light has this property, such as being a wave or a particle, then so does every part of the electromagnetic spectrum. And that's great for us, because then it makes it easier for us to decide on the properties of the electromagnetic spectrum and what it means for us in reality. Okay? Lots to take in. Let's talk about the wave-like nature. We've already spoken a little bit about this. When electromagnetic radiation is formed, it comes from two places, and it's a very, very special wave. Inside the sun, we have a chemical reaction happening. And in fact, it's a nuclear reaction, like with a nuclear bomb. So we have these tiny, minute hydrogen and helium particles that are decaying. They are exploding. Because they're exploding, they are creating charged particles that are moving. Those charged particles create an electric field around them because they are charged. Electric fields come from charged particles. Those charged particles are moving, but we also know, and we're going to deal this a little bit more in electricity, so you're just going to have to bear with me. When a charged particle moves, it also creates a magnetic field. There's a very, very close relationship between electric fields and magnetic fields, okay? So this is why we call this electromagnetic radiation, because it's both electric in nature and magnetic in nature. So it's a little bit of a strange concept. So what I'm going to do now is I'm going to show you an animation, because we can't show you a video because you can't see it. So I'm going to show you an animation, and we're going to talk about where we get this wave nature from, okay? So on this animation, and it's going to go quite quick, but I want you to watch it. You're going to see two parts to it. You're going to see a blue line and you're going to see a red line. So if we play it, now if you look at that, watch, I'm going to stop it there just quickly. What we have there is the red part of the line that you're seeing is the wave that's created because the particle's moving. So the particle moves up and down. As the particle moves up and down, remember from transverse waves, it's a moving motion, so it creates this transverse wave. Okay, so it's creating my crest and my shaft. But electric fields, okay, so this is my electric field that's moving. Electric fields have the special ability to create magnetic fields, and those magnetic fields move perpendicular, so they go at right angles to each other. Okay, so what we have is as the electric field is formed, a magnetic field is formed at the same time. And if we carry on to watch, it's gone through the rest position and it gets through to that point. Now there we see this is a 3D animation, which is great because it's exactly what you've seen. The red line, if you look at it, is a great transverse wave, and at the same time we have the blue magnetic field. So let's just look at that again because it does go rather quickly. Okay, and we can see that as one gets formed, the other gets formed, and it's a really great 3D animation. Let's look at this in a little more detail. We've broken it down into different points. I'm just going to remind you of what we said. So what we have here is the charged particle would start at that point. My charged particle moves up, and as it moves up, this electric field gets made, which we would represent with an E. At the same time, because the electric field is made, my magnetic field is made. That's this, which is a B. That's a new symbol for you guys. You haven't seen that one before. We're not going to do calculations with it, but just so you remember that that means magnetic field. Okay. And let's just remind you what the E means because you haven't seen that one before either. Now, the motion of this charged particle is continuous. It's going to go up and down and up and down and up and down because it's a reaction that's happening inside the sun or whatever we're doing. So here we have it. It's gone a little bit further, and once again, as my electric field gets bigger and bigger and bigger and then smaller and smaller and smaller, at the same time, the magnetic field does exactly the same thing. And they're going to get to their crest at the same time, the peaks here and here. That happens at exactly the same time. It will also be the same size. So what I'm saying to you is that distance and that distance is the same. They're identical in every way. Until eventually we get that beautiful wave that we can see that it's now been turned at right angles, and my blue part is coming out towards me and then away from me, and out towards me and away from me, where we get the crest and the trough from the light. This shows you, especially here, this diagram shows you so nicely, we have a transverse wave. Crests and troughs, okay, wavelength, you remember all those definitions that we've done before, okay, we get amplitude, which also means that these waves have frequency and they have period. So we've now realized that we are making a very, 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 very special transverse wave. They come in twos. Light is this. It is a pair of transverse waves that come at right angles at each other. Okay? This is one of the things that make electromagnetic radiation so, so special. Because it comes in pairs, we're able to actually stop one from moving and still have the other, or we can, depending, and that's what polarization does. We'll discuss that in grade 11 and 12. But this is also why we don't need a medium, because the energy that's moving is electric and magnetic. It doesn't need a medium to move through it. Okay? Quite a difficult thing to get into our heads. But why is this important for us? Because scientists have realized that this wave comes in packets. So it's not like a water wave where you have a little bit and some have a certain, sometimes you get them in a certain energy and sometimes you don't. And oh, it's very random. This comes in packets. So what that means is we get what we call a photon. Now, a photon is a packet of light or a quantum of light. Quantum is a very important word here. Quantum simply means that it comes in specific values, okay? So what scientists have realized is, though the packets can be different sizes depending on what part of the what light we're looking at, whether it's red light, green light, blue light, ultraviolet, infrared, whatever the case may be. But it comes in a very specific pattern. So you'll always find these packets arriving together. Okay? So as it travels through the wave, we get them in packets as a specific value. We're going to talk about photons quite often. Okay? Photons are an interesting little concept. I'm hoping you've heard the word before. In some when you're looking at science fiction again, because they love to go into space, they'll talk about them having phototubes or photon rays or something like that. They're really talking about shooting light at something like a laser. Okay, lasers are great for that. Okay, we've discussed that we have a wave and how it's made, but that means for us that the wave equation is still valid. Okay, my wave equation still very, very valid. V equals frequency times lambda or lambda times frequency. However, when we're talking about the electromagnetic spectrum, specifically with light, this velocity is a very specific value, and it's 3 times 10 to the 8, unless you are told otherwise. But that also means it has a very specific symbol. It is a C. Okay? So when we're looking at equations that require using the wave equation, V equals F times lambda, frequency times wavelength, we actually need to use the velocity of light or the electromagnetic spectrum work in that velocity, and that's C. So let's quickly look at an example. Okay? It says to you, calculate the frequency of an electromagnetic wave with a wavelength of 400 nanometers. Just a quick reminder here, nanometers means that you have 10 to the minus 9 meters. Remember, wavelength must be measured in meters. You can't keep it in nanometers, it's not its SI unit. Let's write down what we know and what we're required. Frequency is what we're asked for. They give you wavelength, which is 400 nanometers, but I can't use it like that. We need to make it meters, so we're just going to times 10 to the minus 9. And now you're probably all going, oh wait, hang on. They want frequency and don't have speed, but they say to you that it's an electromagnetic wave. In fact, this is light because of the wavelength. That means I need to know that C is 3 times 10 to the 8. Okay? This is considered knowledge that you know. It is inferred in the question. So they're not always going to tell you directly what the velocity is, okay? Now, with all of that information, I'm hoping you're all going, we can do that. We've seen questions like this before. Of course you have. C equals F times lambda. C is 3 times 10 to the 8. Frequency is what I'm looking for. And now we have 400 times 10 to the minus 9. In this section of work, you're going to often have to use scientific notation on your calculators. Please make sure you know how to use your calculators properly with how you put the scientific notation in, because that's the biggest problem. Is if you do it wrong, you often get an answer that has too many zeros or doesn't have enough. 3 times 10 to the 8. We're going to divide both sides by 400 times 10 to the minus 9, and we get a ridiculous answer of 7,5 times 10 to the 14 hertz. Huge, huge frequency. This is a tiny, tiny, tiny wave, okay? I can't even make the distance small enough for you to see. So it's a tiny, tiny wave going at an extremely high frequency, okay, which means there's lots of them per second, and it's going really, really fast. Okay, ready for another one? And then we'll take a break. Let's do one more. What is the wavelength? Wavelength of a photon of light, giving you a hint, with a frequency of 101,3 kilohertz. Okay, frequency 101,3 kilohertz. First of all, I can't use kilohertz. Not a chance. Okay? Now you're probably saying, but how do I know how to convert it? Well, think about the fact that if I go from meters to kilometers, I would times by 1,000 times 10 to the 3. Kilo, the K, is times 10 to the 3 as a conversion, which means this is 101,3 times 10 to the 3 hertz. Great. Once again, you're looking at this question going, oh, hang on, no velocity. But your hint, photon of light. That means I know the speed is 3 times 10 to the 8 meters per second. Okay? Great. So, C equals F times lambda. C is 3 times 10 to the 8. My frequency is 101,3 times 10 to the 3. And we're going, oh, we can do this. We've done lights. So this is 3 times 10 to the 8 divided by 101,3 times 10 to the 3. And you get 2961,5 meters. This is a very, very long wave. Okay, this is probably a radio wave. Very, very, very. This is a wave that has a wavelength of over 2 kilometers. That's huge. Okay, so it's a bit of an unusual question. 2 kilometers. Okay, now lots for you to take in, especially for you to think about with the waves and the two waves moving together. So we're going to take a short break. Stretch your legs, get something to drink. When you come back, we're going to look at the electromagnetic spectrum in a little more detail. So we'll see you in a couple of minutes.